Let's continue where we left off in lifting line theory. If you recall, we talked about an elliptic lift distribution, and we got these really useful results. You see that from a three-dimensional wing, as we've discussed, we have induced drag, and now we have a quite simple formula to predict the induced drag, and we noticed that it depended strongly on the weight to lift the airplane and the span. We also saw that the presence of downwash reduced the lift curve slope of a wing as compared to an airfoil, and that to create this elliptic lift distribution, we could really use any shape we wanted. We just have to appropriately twist the wing to make that happen. So today we'll talk about a more general lift distribution and see what makes elliptic potentially desirable. So for the elliptic lift distribution, this was the formula for the circulation. We saw 1 minus 2y over b squared, and with our cosine coordinate transformation in sort of these theta coordinates, this simplified greatly to just sine theta. Well, just like we did in thin airfoil theory, this motivates the use of a Fourier sine series. So again, we're taking kind of this opposite approach where we've got, well, actually here it is too. We have this big equation, fundamental theorem, and we're trying to assume a form of gamma and see what comes out. We assumed elliptic before. Now we're going to assume a more general shape. In fact, with the Fourier series, we could represent potentially anything. And so we're going to make it to be a sum over these sine functions, right? So we're just creating orthogonal functions in this sine series, and an are just coefficients, right? So we could see that this would represent the elliptic case if n was just 1. Normally, though, we like these ans to be non-dimensional, so we're just going to pull out to be v infinity out just to make it non-dimensional. Of course, the 2 doesn't have to be there either. We could choose other things arbitrary. This just makes things a little bit nice. Doesn't matter, right? Because we, of course, could absorb these into the constant. And in the case of the elliptic, right, we put 1 here. We could say that a1 is equal to gamma 0 divided by 2b v infinity. Okay, so but this now allows us to represent any distribution. I'm not going to go through the math because it's really the same as last time. We just plug that into here. We take derivatives, and do the same process as we did last time. We can work out this angle, the downwash, then the induced angle attack, from which we can get the induced drag. But if we do that, this is what we get. Induced drag coefficient is equal to CL squared over pi aspect ratio. So that part looks exactly the same as what we had last time. Then we've got this sum here, n equals 1 to big N, depending on how many coefficients we chose to include, n times an over a1 squared. Okay, so what we see is that if I omit this term, this is exactly what we have with the elliptic. In other words, elliptic is the case where this is equal to 1. If I look at this term more closely, I can see that it's going to be, as I start summing these, 1 times something squared plus 2 times something squared plus 3 times something squared. This is going to be a number that is greater than or equal to 1, right? Yeah, so these are just going to, so actually the first term is exactly 1, right? Because it's a1 over a1 squared. So it's something bigger than 1 is all we know. In other words, the elliptic case is when there's only n equals 1, right? That's this case. And so all of these are gone. All of these other terms are gone for the elliptic case. So we can see that the elliptic lift distribution gives us the minimum induced drag, because any other terms that appear, anything that deviates from elliptic, and we need to add additional terms in our Fourier series, is going to add additional terms in computing our induced drag. So to state that again, elliptic lift distribution is the minimum induced drag solution. And I should add really for a planar wing and a fixed span. But so planar wing means it's on a flat plane, right? We don't have winglets or things. We can, with non-planar wings, actually reduce an induced drag without having an elliptic lift distribution. But for a planar wing, this is the minimum induced drag solution. Now this big term, we typically wrap it all up. This thing here, we wrap it up into one big factor. And because this is all greater than or equal to 1, if I take the inverse, it'll be something less than or equal to 1. And that's the way we usually write it. So we'll write a formula like this: CL squared over pi aspect ratio times E inviscid. And the reason why we like that is that now E inviscid is a number that's less than or equal to 1. So it's kind of like an efficiency. In fact, this is called the Inviscid span efficiency. As we've seen, it'll be less than or equal to 1, something between 0 and 1. So it's like an efficiency. And the definition is just as we've seen here. It's just take that thing in the brackets and invert it. So more explicitly, the sum of n times n over a1 squared. So that's what it'd be if we were actually using lifting line theory, although this formula is true in general. This just tells us the relationship between our lift coefficient, our induced drag coefficient, and this is just, often we just use this directly. We compute the Inviscid span efficiency. So for example, in the homework, we compute the lift, we compute the drag, and we can then figure out what our Inviscid span efficiency is and see how close we are to elliptic, for example. Like before, the dimensional version is often quite helpful, especially if you want to see what parameters most strongly affect induced drag. And as before, it's exactly the same, except for now we have the addition of the E inviscid term here in the denominator. Okay, so again, big takeaway, elliptic lift distribution is the minimum induced drag solution. This is why many airplanes use something close to an elliptic lift distribution. We usually don't get that exactly for various reasons. One is aerodynamics or induced drag isn't necessarily everything. And so we often want to actually bring the load distribution a little bit more inboard. We don't lose much on the induced drag, but we can alleviate some of the bending loads on the wing, so we can reduce some structural weight, and that often can have more significant impact than the small change in induced drag. We won't get into that in this class, but you can see a formula for how the centroid varies. And as expected with a minimum, right, that this is going to be fairly flat near the minimum. So small deviations don't do much for changing the Inviscid span efficiency, but they do have a bigger effect on the lift centroid. So if we're thinking about a more system level objective, then often we want to skew the lift inboard somewhat, but not by a huge amount, right? So we do generally strive to have a lift distribution that's pretty close to elliptic. One difference from thin airfoil theory is that in thin airfoil theory, we can compute each coefficient one at a time. So we can compute, the first one and the second one, and then we could stop whenever, it seemed like they were becoming really small and they weren't contributing much. In this method, they're all coupled, so we have to choose how many coefficients we want beforehand, and we have to solve them all simultaneously. We can, of course, redo that, but we can't just reuse the coefficients we already have. We'd have to start them all over if we wanted more coefficients and solve them all simultaneously again. We won't do that in the homework, but if you want to do that, right, we just plug these things in to this thing. And if you use a small angle approximation, for example, you would get something like this, that alpha minus alpha 0 is equal to 2b pi c. Again, we're not going to do this in the homework. We're going to use the vortex lattice method, which we'll discuss later, which is potentially a little bit more versatile. They each have some advantages, but certainly a commonly used approach. Right, so here's kind of that same equation. We've plugged everything in, and we have to use a collocation method. So what you would do is, I'll just show, you could use symmetry, but I'll just show, say with a straight wing here, without any symmetries. Let's say this is my midplane here. I would have to pick endpoints. So if I had n equation, let's say I decided I was going to have 12 coefficients, that's what I needed to represent my Fourier series well, then I would have endpoints, evenly spaced here to, I'm only going to draw 6. So let's just say I had 6 coefficients. Then I'd have 6 points. I'd evaluate this equation. So I'd have 6 equations and 6 unknowns, and I could solve for all of those. Okay, so, but again, we're not going to do that. I actually want to talk about a few other concepts that might find useful here related to lifting line theory. So one is another way we could look at determining that the elliptic drag, or sorry, the elliptic lift distribution is the minimum induced drag. It can also help us give some other additional insights. This is using this method of restricted variations. R.T. Jones published some papers where he extended this to look at other things, bending moment constraints, and so on. We're going to look at a really simple case. And the idea is this. Imagine that I have a lift distribution, and it could be any shape, which is arbitrary, right? And I want to modify it, perturb it, make infinitesimal variations until I can get towards an optimal, the minimum drag solution. So for example, in this little cartoon here, let's say I took out some small chunk of circulation at some point and maybe added it or changed another part somewhere else, right? So I'm just going to make these small perturbations, arbitrary locations on the wing of arbitrary amounts. Well, I need to make the changes such that the lift is zero. The total change in lift should be zero. I need to maintain my lift. So if I take out something somewhere, I'm going to have to add it somewhere else. So in other words, d gamma 1 plus d gamma 2 must be equal to 0. Okay, so for minimum drag, though, I also want the change in induced drag to be 0, right? So remember from calculus that if I'm varying, let's say this is induced drag, to be at a minimum, that means that my slope here is 0, right? So I want also this change in induced drag to be 0. Well, we've seen from the Kutta-Joukowski theorem, what if this is my, this is V infinity, this is my downwash, this is lift, and this is now my induced drag, that the induced drag here I could get from rho W cross gamma, right? That's my induced drag from the Kutta-Joukowski. Rho, we're going to assume is constant between this station and this station. So to have the change in induced drag to be 0, I just need the downwash 1 times d gamma 1 plus the downwash at 2 d gamma 2 to equal to 0, right? So I just took the change in drag at the station plus the change in drag at this station according to this formula and set them equal to 0. I could have put a rho in there, right? That would just cancel out. All right, so I have two equations, two unknowns. So this says for fixed lift and minimum induced drag, these are my criteria. And if I just substitute that one into here, what I get is that W1 equals W2. So the downwash at 1 is equal to the downwash at 2, because 1 and 2 are just arbitrary locations, right? They could be anywhere on the wing. That means that for minimum induced drag, I need my downwash to be constant along the wing. And as we saw last time, the elliptic lift distribution does produce constant downwash, and so that is the minimum induced drag solution. Of course, we already knew that, but this same method can be useful to show us other things. So for example, let's imagine I have a non-planar wing. So here I'm going to increase the dihedral, perhaps all the way vertical, like in this case, so I've got a wing with a winglet. Well, let's look at what a winglet does. So one thing that you'll sometimes hear, let's use the Kutta-Joukowski theorem a few times here. So let's say this is a back view of our winglet. And so the wing, imagine I've got this wing, right? And it produces, as we've seen, kind of these trailing vortices, a pair of counter-rotating vortices. So here I'm just drawing one of them on the right side of the wing. So if I now add this winglet here, right, you can see that that vortex is going to be pushing on that winglet. It's going to induce a velocity that's going sideways, right to left here on that winglet. So now if I was to draw a top view, here's going towards my wingtip, and here's my winglet on my wing. So it's vertical, and I'm just seeing this airfoil here. Well, the airplane's flying forward, so there's a free stream velocity coming in. And because of this vortex that the wing generates, I get this sideways component. This is just the induced velocity from the wing, right? And so my total relative velocity is now this way, right? It's not just straight on, but because of the sideways component, it's now coming at an angle. Well, remember Kutta-Joukowski is rho v gamma, or rho v cross gamma, right? That the force that's produced is rho v cross gamma. So we have the direction of v, here's v, but what's the direction of gamma? Well, again, let's think about the top view. Here's a top view of a wing, right? And if we drew like a little horseshoe vortex, recall the direction, gamma looks like this, right? And it kind of continues along same direction all the way around the wing. So if you put your thumb in the direction of the arrow and curl your fingers, that points in the induced velocity. So there's downwash here in the middle, right? This one, I put my thumb, it's pushing down, forward is pushing down, right? They're all pushing down. So this formula, right? If you remember Kaczykowski, if this is V infinity coming in, gamma's to the right, so V cross gamma gives me a force up, that's my lift. Well, winglet's gonna be the same. So let's imagine I've got this wing here, and now I rotate it 90 degrees. So before the straight wing, my circulation was going left to right. So now if I rotate that, gamma is now pointing up here on this view here. So gamma is up out of the page. So V cross gamma gives me a force perpendicular to that like this, right? So if this is a right angle like this, that's the force that's introduced. And if I did it on the other side, so let me just erase this real quick. Here's the other half of my wing over here. Right, we get the exact same thing, only just opposite. V would be like this, and I get a force this way. So they'd be exactly the same. So these two sideways components would cancel out, but I have a component that's facing forward. In other words, it's a component of thrust. And this is one explanation we sometimes hear about winglets, that the purpose of a winglet is that it generates this induced thrust, right? So that's going to reduce your induced drag. Okay, so that sounds good. It turns out, though, that's actually not optimal. It's not an optimal use of a winglet. You could definitely do that. You could have the winglet generate some induced thrust, but it's actually not optimal. We can see that if we go back to this derivation, and let's just repeat it one more time. But now for this case where I could have, this dihedral here, everything is not non-planar. So now, I have some circulation. There's a gamma 1 here, gamma 2 at arbitrary points. The lift is actually only the vertical component, right? Any horizontal component doesn't contribute to the lift. So if I want my change in lift to be 0, I need delta gamma 1 times the cosine of that dihedral plus delta gamma 2 times the cosine of the dihedral to be 0, right? Because I have to take the cosine to get the vertical component of my lift. All right, so again, if it's flat, cosine of 0 is just 1, it's unchanged. The induced drag equation is the same, except for instead of downwash, we use normal wash. Remember, normal wash is the induced velocity. Actually, I'm not sure that we've talked about that yet. We will be soon. So the general case is that downwash for a planar wing, that's what matters. But induced drag, what matters in general is not the velocity downward, but actually perpendicular or normal to the surface. So in this case, it would look that way. So we'll just write it like that. Induced drag is 0. So we can say rho times the normal wash at 1 times delta gamma 1 plus rho normal wash at 2 delta gamma 2 0. So for minimum induced drag, the equation looks exactly the same. We just replaced normal wash, or we replaced the downwash with normal wash. So again, we just combine these two equations, and what we get is that the normal wash has to be equal to some constant times the cosine of the angle. So in other words, for minimum induced drag, the downwash should vary with the cosine of the angle. So again, if the cosine was 0 everywhere, flat wing, that would mean the normal wash should be everywhere constant, which is what we just saw before, right? Constant downwash along the wing. But not necessarily the case, or not so with dihedral. Specifically, if we look at a vertical winglet, phi is 90 degrees in that case. And that says that for optimal loading, the normal wash, the net normal wash of the winglet should be 0. This is not net 0, right? So there's an induced velocity that is non-zero. So actually what we would like for optimal loading is for the winglet to look something like this, right? So I've got still, of course, V infinity, I'm flying forward. And I still have this induced velocity from the wing, that still exists. But what I'd like is for the downwash of the winglet on itself to exactly cancel out. So actually, let's look at that first. Let's go back and think about a regular wing again. Easier to see on a regular wing, just planar. Right, here's our simple horseshoe vortex in the direction of gamma. And remember, it's inducing a velocity downward on itself, right? So if I looked at, just for example, this bound vortex, it's inducing a velocity downward. Actually, all of these are, right? Are inducing a downward velocity on the wing on itself. So again, take that wing, rotate it 90 degrees. Now it's a winglet. So what direction is the winglet inducing on itself? It's downward still, but now that's left to right. So this is now from the winglet, oops, on itself. Okay. So I've got the free stream velocity. I've got the induced velocity from the wing on the winglet and the induced velocity from the winglet on itself. And for optimal loading, what I would like is for the induced velocity from the winglet on itself and the wing on the winglet to exactly cancel so that the net normal wash was 0. That's a non-intuitive result, perhaps, right? Because this actually means the winglet does not generate induced thrust. Total velocity is now just downward. So the perpendicular force is downwards or perpendicular, sorry, not downwards, it's perpendicular to the winglet. No induced thrust. So how could that be better, right? I mean, we said that this is optimal, but clearly having some induced thrust is better than having no thrust. Well, the reason why this is actually better is because we have only so far looked at the winglet. We haven't thought about the winglet system, right? So even though the winglet is maybe not getting as much benefit here or any real benefit, the winglet does affect the wing. So we have to look at the downwash of the wing on itself, which we already know is downwards. But how now does the winglet affect the wing? So if we look here again in our side view, let's imagine this case again, right? The winglet, it induces a downwash on itself. So the circulation, remember here, is going left to right. So I rotate that, now it's going vertical. So I've got kind of this circulation. Here's my winglet in this side view, and it's generating a downwash on itself. So there's this horseshoe vortex. Well, this is a little bit hard to draw. Let's see, how do I draw this? Let's think about this trailing vortex, perhaps. Maybe that's easier. In this case, it'd be going down, and no, actually, no, I still do want to do that bound vortex. It's going to be, let's see, what's the best way? No, actually, sorry, I'm making this more confusing than it needs to be. Let's think about this one. This is the one that's closest, right? Because if I take that wing and rotate it, all of them are going to have an effect. But the one that's closest, kind of the biggest effect, is going to be this one. So let's just consider that. So if I rotate it, it's going like this. It's still going to be going now in this side view into the page. So the winglet is generating a vortex that's going into the page. So it's kind of like this. This is the direction of the induced circulation from that one bound vortex. So I know this takes a little bit to visualize. You might have to sit down with this and try this, but for this normal loading here, right, like this vortex here, we rotated it, and now we're looking at a sideways view. So when I rotated it, it's going from out to in and out of the page here. So that's like this direction here. So the winglet, as shown, is now inducing an upwash on the wing. So that's going to reduce the induced drag on the wing. So in other words, with this type of optimal loading, I've kind of increased the loading on the winglet such that it's not really getting any benefit, but it's generating more circulation that actually helps the wing. So overall, the winglet system, my entire wing, right, actually gets a net induced drag benefit, even though the winglet is not really generating a component of thrust. It's really better, rather than trying to use the wing to help the winglet, to use the winglet to help the wing, which kind of makes sense, right? Because the wing is really what's doing much more of the work, or really all the work in terms of generating the lift. Any lift the winglet generates, especially for 90 degrees, is not helpful, right? So sideways force is really used here to kind of alleviate some loading on the winglet or the wing. All right, one more thing, just to kind of close a loose end here. So what we've seen so far is that we've had the simple model, and actually we made it a little more complicated, but I'm just going to draw with one horseshoe vortex for now. We took this wing, put a horseshoe vortex on it, and actually we extended it, right, so that there's an infinite number, but let's just draw that for now. For the one for now, it's the same idea. So we've got trilling vortices and a bound vortex. Actually, yeah, we will consider all of them because that's what we've done. So we've got all these trailing vortices, infinite number of them. And what I want to plot is the contribution of the velocity, or the downwash. We'll just consider a planar case downwash, as I go very far in front of the wing, to the wing, and very far downstream. Well, we already computed this for the trailing vortices, right? If I go very far away, I'm way up here, those trailing vortices should approach 0, right? So let's use blue. I'm gonna erase this bound and make that one red because this is gonna have different colors. Okay, that's the bound. So blue is the trailing vortex. It should be close to 0 as I'm very far away. But what we saw, this was actually exactly what we computed, right? We took this model here, we calculated the influence of a trailing vortex and integrated to compute all the trailing vortices. Notice actually that we never talked about the bound vortex. And now we're going to discuss if that's actually problematic or not, because we didn't include that. If we had a very simple case, right, this planar wing, the bound vortex would induce no velocity on itself because the center of the bound vortex would pass to this point. So that's one way to justify it. But what about a more general case, right? We've generated this formula based on lifting line theory. Does this only work for a planar, flat, no sweep, very simple wing, or is it a bit more general? Well, let's see. So we calculated this for the trailing vortex, and we saw that at least for the elliptic case, the downwash angle was, proportional to CL pi aspect ratio. This is actually the tangent of the induced angle, which is not exactly the downwash. It's close, right? Because let's see, where do we write that, right? It's, well, if we multiply by V infinity, it is, right? The tangent of the angle. Tangent of our induced angle times V infinity is the downwash. So actually it is exactly that because I've normalized this by V infinity. Sorry, I'm flipping through a lot right here, right? So this is what we computed. This is the downwash right here along the wing from all those trailing vortices. So it varies from 0 far away and approaches this value here, which we computed. Although we didn't compute it very far downstream, you could guess what it is, right? Because when I'm here, the contribution is a contribution from a bunch of semi-infinite vortices. If I go very far downstream, it becomes a contribution of an infinite vortices, right? Because they vary infinitely in both directions, again, if I go far enough away. So the induced velocity from all those trailing vortices as they go further away is going to asymptotically approach twice that value. In other words, the velocity induced in the far field is going to be twice that of what we compute here in the near field. However, now I have this bound vortex, right? I've got that as well, and I didn't really think about that too much. But if I looked at the side view, that bound vortex looks like this, right? So again, far away, of course, it does nothing. But as I get very close to the wing, it's going to generate a huge upwash, right? So it's going to look something like this. And then on the other side, nothing very far away, but as I get close, it's going to generate this huge downwash. So it'll look something like this, right? And now if I was to look at the total, I have to add those together because they both matter. And, it looks something like, I don't know, this, and this one would asymptotically go to the same point here and then kind of get bigger over here. So that's the total in green. So we have a parent problem in that our whole induced drag formula we based on the fact that the downwash was, or the this value here, the downwash normalized by infinity was CL over pi aspect ratio. But what we see is that it's not really that. That's only the case if there's only trailing vortices. If we include the bound vortices, then that's not really what the downwash is here at the wing. It is in the far field. That still works, right? Notice that the bound vortex goes away. So on the far field, we get 2 times CL over pi aspect ratio. But right at the wing, right, the bound vortex is really going to mess things up. So fortunately, though, this still works for computing induced drag. It does mean that my induced velocity is actually wrong, right? It's not actually just CL over pi aspect ratio. I'd have to include that bound vortex, but the induced drag that we calculated is still correct. And here's why. Let's imagine a generic case. Here's an airfoil, and it's got a bunch of bound vorticity. We could lump it all up into one bound vortex, but we could also think about many just bound vortices, or this could be, you think about a swept wing where the bound vortex is varying, or sorry, has different segments or whatever. Let me just consider any 2 arbitrary components of these bound vortices. Let's think about how does gamma 2 affect gamma 1? Which way, what direction is the velocity that induces? Well, given the direction of gamma 2, over here on the left, it's going to induce a velocity upward, right? And its magnitude, as we've seen for an infinite vortex, is gamma over 2 pi r, right? The bound vortex is not necessarily infinite, but this is, let's just approximate for now. It would be modified somewhat, but it would be modified by the same amount for all of them. So this would be, let's say, gamma over 2 pi r if we consider this infinite, where r is this distance here. That's the direction of the velocity induces. And then from Kutaijikowski, let's think about the force. So this is a vortex. It's got some strength gamma, and there's some velocity being here that's of this strength or magnitude this. So if I take V up, crossed into gamma, so if I curl my fingers around gamma, my thumb is into the page, so that's the direction of gamma. So V up, cross gamma in. This is generating a force, an induced drag, whose magnitude is going to be rho times V times this gamma. So that's going to be gamma 2 over 2 pi r times gamma 1. Now let's think about the other case here. Gamma 1 now affects gamma 2, and because of the direction of this vortex, it induces a downward velocity. Its magnitude is gamma 1 over 2 pi r, and then the force that gets generated, right, notice gamma is still into the page here, so V down, cross gamma into the page, gives me a force to the right, and its magnitude is rho times V, which is gamma 1 over 2 pi r, times its gamma, which is gamma 2. And so we notice that this is exactly equal and opposite to that, and that's true of any pairs of boundwise vortices. So we could have any number of them, and if we consider the contribution from any, we could pair up every single one to sum them all up, and they will always cancel. So this one will cancel the effect of this on that and this on that. The effects on each other always cancel for drag. So in other words, for computing induced drag, what we've done is correct. It'll give us the right answer, even though the downwash is not actually right. And even though we did that Kutaijikowski thing, where we said, drew an airfoil, and we said, oh, it's just like V infinity, and then we could calculate the downwash. And from that downwash, we could use Kutaijikowski and get lift and drag. Well, we just showed that downwash is not actually correct. The magnitude is different. It's not CL over pi aspect ratio, it's modified. But turns out for computing induced drag, this still works, still gives us the right answer, because all these bound vortices will always cancel out. The contributions to each other, the sum will always cancel to 0. So actually what we've done will still give us the right answer, even though the model is a little bit flawed. It actually does still work. And Monk was the one who showed this idea of these bound vortices canceling. Okay, so that's really the last idea here. And this does mean that this formula here is quite general, even though we've derived it under some very specific case with just a straight wing. This is a general formula we can use, and very useful. We don't have to use lifting line theory to compute this per se. So as we'll see, we'll just compute lift and drag with other methods like vortex lattice that we'll talk about next time. And we could then look at our Inviscid. Elliptic has an Inviscid of 1. That's our minimum drag solution. All right, so we'll look next time at some numerical approaches, kind of like as we went from thin airfoil theory to a panel code, we'll kind of do the same thing. This lifting line theory, like thin airfoil theory, gave us some really useful analytic expressions that we could get from doing the integrals analytically. We got these formulas for induced drag. We got some insights into some approximate formulas for lift curve slope. Now we're going to go look at a numerical method, somewhat like the panel method we did for airfoils, but now we're going to be able to solve lift distributions and induced drag for wings.